All right, here we go. So what I want you guys to think about is we're gonna start to do integration.
This is 5.2.
Yeah, this is chapter 5. So we're gonna start to do integration. So what we've been doing up to this point, integration is like the inverse operation of derivatives. And you'll see why when I go through this. So what we've been doing with regards to derivatives, derivatives tell us a couple of things. If I have a function, okay, and I take the first derivative, f prime,
X squared.
and then I take the second derivative, I learned some stuff. The first thing that I learned, this tells me the slope of the tangent line at a particular point. Which in essence tells me if it's increasing or decreasing. Okay? And graphically speaking. And f double prime basically tells me concavity and points of inflection. But the point of inflection is just when the concavity changes. So it'll tell me if it's curling down or curling up. Now, when we draw the graph, we're thinking that's how I sketch the graph. That's how I draw the graph. But really, what we see graphically when we graph these functions, we see the behavior. We see the numbers increasing or decreasing. They can increase faster or slower. And that's what all this stuff means. Okay? That's what we get from that. What we use it in the real world is a lot of business models are interested in when things increase or decrease, and they make adjustments accordingly. We use it in ecological models because we study populations, and we want to know when the population growth is increasing or decreasing for various reasons, especially endangered species. We study it in science based on the strength of a material, whether it increases or decreases depending upon how much temperature or pressure is added, things of that nature. And electronics, we study the same behavior. Basically everything, there's math where we count things, and sometimes things change, and they either increase or decrease, and they can increase rapidly, or they can increase slowly, or they can decrease. And all this is based on derivatives at a point. So if you have one value that's dependent upon another value, a y dependent upon an x value, we can study that behavior using calculus at any particular point, at an instantaneous value of x. Okay? Integration goes backwards. If I say f double prime of x is equal to 6x, and I integrate f double prime of x, that's what the swirl means. And this is very informal. I'm leaving out some key details, but I just kind of want to introduce you to things slowly. Then that gives me f prime of x
Should it be a plus like C or something?
Yeah, there's got to be a plus C and all that stuff. So we're going to assume that C is 0. I'm glad that you remembered that. Yeah. And technically, I should start throwing this in too to be just a little more formal. This is a derivative with respect to x. And then, if I say So this equals F. This equals F prime, or F single prime. And we'll get to that. Yes?
So the part that I don't get is why you put the dx in the back of it. Like,
because, well, we're remembering that it's a function of x and that this really represents a derivative with respect to x.
okay, so just telling you what it is.
Yeah. Because just like, remember before when we took the derivative of something, we could take the derivative with respect to t, we could take the derivative with respect to x. And same with integration. I can integrate with respect to x, I can integrate with respect to t. How would I know? Well, this stuff here. Okay? That's saying I want you to take derivative with respect to x. In most cases. Well, at least in your high school AP calculus class. Okay. So now, that works backwards, but here's the interesting thing. What we really end up doing is that does something graphically. When we integrate something, we actually get the area under the curve. So integration actually gives us a numerical value that represents the area under the curve. Okay? So consider the following function. Let's say that f of x is equal to x squared plus 4. And we all know that that is a parabola with the y-intercept of 4. Okay? Now, what does that look like graphically? It looks like this. Now I'm going to show you the notation. I'm going to kind of do it informally. We're not going to crank through and do the actual exact value area under the curve, but I want to slowly start to introduce you to it. So what I want to do is I want to figure out the area under the curve from these 2 points, and I'm going to choose A equals 2, B equals 4. Now what that means is the notation kind of looks like this. Okay? And this will be the area under the curve. So that's what I'm going to end up teaching you eventually. It's calculus, but we're going to take the antiderivative and then evaluate from 4 to 2, and that gives us the exact area under the curve. Now when I say area under the curve, what I'm talking about is this right here. Area under the curve is from the curve to the x-axis. Well, what do you notice? Well, what I notice is that this is a curve. How do you calculate the area of a shape that isn't quite a polygon?
Irregular polygon.
This looks like it's going to get really hard really quick.
Yeah, it looks difficult, but it's easier than it looks. So, one way to do it is to take it, if I were to say, could I calculate the area of that rectangle? And could I calculate the area of this rectangle? Would that be a pretty good approximation of the area under the curve?
I guess.
It would be. It would be a little bit less than the actual area under the curve because I'm forgetting about these two things. All right, calculate the area under the curve. How do I do that?
Base times height.
Yeah, base times height. So he said, well, that's easy, Mr. Adams. That's just the base times the height. All right, what's the base?
Base is 1.
Base is
Well,
1.
both.
Okay, great. The base, if I make them the same width, the base will be 1 in both cases, right? So, but I'm going to use some different notation. really where the 1 comes from, delta x is equal to 3, because this is 3 right here, minus 2, which is 1, and then, is that right?
Yep.
When I'm talking about the x direction, that's how I measure the base. Does that make sense to you guys? Okay. All right, so I'm going to say delta x times the height, right? I'm going to do something a little different though. Why don't we, because it's more than one rectangle, right? Why don't I do something like this? And that would be delta x times the height. Now here's why I wrote it that way, and this is x, delta x times. How do I figure out this height here? That's right here. Wait, isn't that like x sub 1 comma f of x sub 1?
Yeah.
Huh?
Yeah? So the height is what? The y value, right?
Yeah.
But since we're being all formal, you slid down in your chair.
It's over.
It's over? So the height is the y value, and the y value is f of x, right? Right?
And the wink face.
And in the winky face,
Bring out the smiley face and the winky face.
now this height here is x sub 2 comma f of x sub 2. Right? It's just x comma y. This point right here. The height, in other words, the height of this rectangle is whatever the y value is for this. So we've got like x comma y. Right? So now by doing the summation notation, what I'm saying is that the height will always be f of x I.
Why?
Is the I an imaginary number?
You literally just made up half of those equations and symbols right now. I swear. They're not real.
What is that? That's not real. It's
I know that you guys are anxious. Just take a deep breath. In with the good air. Out with the bad air. We're going to crane through it in a second on the next page.
we just did.
It's not correct.
Yes.
Explain all those.
All the notation. Yes, I will. Yes.
Oh, what does I mean?
So the question is, oh, that's nice, Mr. Adams. You're a mathematician. But what the heck does all this stuff mean?
Oh yeah. Oh, that was an I? I thought that was like a spell.
Just had to ask a question.
Well, in this particular case, we said, oh, this is an x of I, it's just delta x.
Yeah.
In this particular case, we said a couple of things. We said that delta x is equal to 1. Now, when I write it this way, really what I'm writing is, this is delta x times x sub 1. And in fact, we're only going to do 2 scenarios on this first one. All right? Now that's summation notation, which means we're summing up a bunch of stuff. So now that's plus delta x. What comes after 1?
2.
2. Times f of x sub 2. So this is a shortcut way of saying I'm going to have delta x times the y value plus delta x times the next y value plus delta x times the next y value plus delta x times the next y value. We kind of covered this last year in pre-calc. Okay, yes?
What is the 2 on top?
Oh, it says keep plugging in numbers, and this is the last number you plug in.
Oh.
Okay? So we're going to come back to that. But if I were to do something like this, this is the beginning number, and I'm going kind of informal on purpose. and this is the final number.
If this is informal, how bad is formal?
Well, there's other terms, but so this would be x sub 1 squared plus x sub 2 squared plus x sub 3. When do I stop doing this?
4.
4. That's all that means. We did this last year. You guys don't remember. It was right at the end. The sun was shining. It was almost summertime. You guys wanted to go to the
That's
beach.
why.
Nobody was paying attention to Mr. Adams. All right. So that's what that means. Is it coming back to you now?
Wait, what's the I?
No.
The I just tells us where to put the numbers in there. Yeah, like this is I, right? So this is 1, 2, 3.
But I need below that.
This is the starting number. My first number is 1. I equals 1.
Okay.
So if you had I equals 2, then instead of 2.
Yeah, so like if I change this right here, if I change this to like I equals 2, then we would only do this. Does that make sense? We could start and stop wherever we want.
So we stop here.
You want to stop here? Nice try. Back to the problem at hand. We're trying to calculate the area under the curve by finding the area of the two rectangles that are bound by the function x squared plus 4. And this is where we're at. So, how do I find this number? Well, we've got to come back here. What would be x sub 1? X sub 1 is equal to
2.
2. X sub 2 is equal to
3.
3. Now that you just got to put on your thinking caps. I'll show you a little more formal way, but that's put on your thinking caps.
I like that.
So, here's a trick though. If I'm adding this up, what do you notice about these terms?
They are the same.
They're the same. Could I rewrite that as delta x times the quantity f sub x? Wow. Let's just write it out. F of x sub 1 plus f of x sub 2. Like that?
Yes, you could.
Yep. So delta x was 1, and then we have f of 2 plus f of 3. Is that right?
Yeah.
Wait. What happened to slowly introducing us?
This is the slope. Alright, so now f of 2, remember that this is x squared plus 4, so we're going to say 2 squared plus 4, which is 8. And then f of 3 is 3 squared plus 4, which is 13, right? Is that right? Yeah?
Yeah.
Why is it 2 and 3?
That's the one that's
Because this is 2 and this is 3, based on how we drew our graph and where we wanted the rectangles to be. Is that right?
The y is 2 and 3?
No, the x values are 2 and 3, and we're getting the y value by plugging it into the equation. Okay? So to find the area under the curve, we know the base. This base, let me highlight some things. The base, delta x, is from here to here and from here to here, and that's the same. That's 1. Now what I want to do is I want to calculate, let me find a different color, pink. I want to calculate this length here. Well, that length is f of 2, right? Because it's the y value of that point on the curve, isn't it? So that's why this is why we're doing f of 2. And then we do the same thing for the other rectangle, which is f of 3. Because if we come back here, whoops. If we come back here, let's do this one. This length here is the y value f of x sub 2, which is 3. Okay? All right, you guys good so far? So now to approximate the area under the curve, because that's what this is, we have 1 times 8 plus 13, which is 21.
21.
Okay? Does that make sense? Now what we're saying is, I'm going to draw a bunch of stuff. What we're saying is that if I have my graph of my function, where this is 2, 3, 4, and f of x is equal to x squared plus 4, that the area of this rectangle is 8 and the area of this rectangle is 13. So then the approximate value from 2 to 4, or actually I wrote it backwards. Is that right? Is that right?
Yep.
There's 21. Okay? But when we did that, it's not exactly what it is because I've got those little triangles that we didn't calculate. Does that make sense? Okay.
Is that all you would do?
Well, I have a question for you guys. How can I be more precise? How can I be more precise?
Try and get the triangle?
Yeah, we want to make those triangles kind of go away. We could calculate the area of the triangles, which you could do, but that's a lot of math. But we want to look for an easier way, which would mean make the size of the triangles smaller. So here's what I propose. Watch what I'm about to do. You guys ready? Same graph. We said we did something like this, and something like this, and something like this, right? What if I were to make 4 rectangles? What if I were to do like this?
That would be a lot of rectangles.
I don't think that's a good idea.
Well, it's not as difficult as you think. But what I notice is, look, now my triangles are much smaller. So if I were to do that, and this is 3, what's this number here?
2.5.
2.5. What's this number here?
3.5.
3.5. Okay, so are you guys ready?
Yeah.
So now what we're going to do is we're going to try to approximate the area under the curve of x squared plus 4, okay, which is approximately the sum of, we're going to start at 1 and go to, how many rectangles do we have?
4.
4. Which is still delta x times f of x sub I, which is equal to delta x times f of 1, x sub 1 plus f of x sub 2, which is plus f of x sub 3.
Whoa.
I need a little room there, which is equal or plus f of x sub 4. A couple changes though. What's delta x?
Delta x.
Delta x is this stuff here. So delta x is equal to what now? 0.5. So I've got 0.5 times f of, what's my first x value?
2.
2. What's my second x value?
2.5.
2.5. What's my next x value?
13. Or no, 3.
And then my next x value?
3.5.
Now, it may seem hard, but I can calculate that. we're going to cheat a little bit. I know that you guys know how to evaluate that. I'm not going to have you guys waste your time and by hand write out f of 2, f of 2.5. I'm not going to have you guys do that. We can use our calculator for that now. So I'm going to turn my calculator on, and here's the easy way to do this.
Graph it.
Not graph it, we'll use the table.
Well, yeah. You gotta graph it first.
I'm sorry, I thought I was teaching.
Apparently
Nope.
Zach's teaching now.
I could sit down, I would like to. Oh, I showed you the answer, Bennett. Delete it, clear. You
We
see
do
it.
graph it.
All right, so what I want to do is, I forgot I did this last hour. What I want to do is I'm going to let my calculator, watch this, I'm going to let my calculator graph it for me and calculate the answer. So I plug in x squared plus 4 and y sub 1. Okay. Then I'm going to hit second window. Okay. And I'm going to start with the number 2. And what's delta x? 0.5. So what do you think I should set my delta table to?
0.5.
0.5.
0.5. Watch what happens when I do that.
Goes to 0.5.
What? What? All right. So then I have my numbers here, right? 8, 10.25, 13, and 16.25. Those are all the y values evaluated at the corresponding x values. Does that make sense? See what I did? Do you have a question? Okay. That's all right.
You plugged in the y equals, you plugged x squared plus 4.
Mm-hmm.
And where did you get 0.5?
Delta x. So delta x, now, see this? I'm calculating the area under the curve, but my base has changed to 0.5.
Oh, between the two.
Yeah. And then this is 0.5. And then this is 0.5, and this is 0.5. Yep. So now I've got these values. It was 8 plus 10.25 plus 13 plus, what was it? 16.25?
Yeah.
16.25. And I'm going to plug this in my calculator and see what did we have last time? 21?
21. We should have
21.
23.
So now if I plug that in my calculator, which I did last hour, what do I get?
33.7.
No. This is something else. We did 5. Wait, I was trying to show them something. But I get 23.75,
Yes.
right?
Yep.
Yeah.
So now what I'm saying is that the area under the curve
Is 23.
is approximately 23.75. But that's an approximation. It's not the exact value. So now, what did we do? We said the problem with our approximation is that we've got these little triangles. This wasn't too much more complicated to calculate than the previous example. But we had a more precise answer. If I wanted to get really close to the exact area under the curve, what would you do?
Split it into a million pieces.
Okay, so how do we split it into a million? She said split it into a million rectangles. How do I do that?
Calculate her.
What changes?
X or delta x.
Tell me if this sounds familiar. We want delta x to approach what value?
Infinity.
No,
No.
0.
0.
0. Oh.
Which gives us infinitely many rectangles. Does that sound familiar?
Not really.
Now what your calculator does, and I'll show you how to do this, but I'm only showing you how to do this because I want you to double check your answer. There's a process to do this that will give you the exact value. I'm not going to teach that to you just yet. But what your calculator will do is your calculator will find the area under the curve by letting delta x equal a very, 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 very small number. I don't know what the exact value is, but they will plug in a very, very, very small number and they will go through that process. What I just showed you was like kind of Riemann sums. We'll talk about it a little more formally on Monday. Riemann's a smart dude. So anyways, let's see what it is on the calculator. Now we went from 21 to 23.75. If I graph it on the calculator, I can actually, but that's what we're looking at is the area under the curve. So the purple line is the graph, and we're trying to calculate the shaded purple region. So how do I do that? I hit second, trace, which pulls up the calculate menu. What option would you choose?
7.
Probably 6.
7.
7 is the correct answer.
Yeah.
So what's our lower limit?
0.
2.
2. What's our upper limit?
4.
4. Now what your calculator will do is it'll make delta x a very, 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 very small number, and then it calculates it. And it's the actual value is 26.66 or 26 2/3. All right. So the actual value Now here's what I want to show you guys. Are you ready to have your mind blown here?
No.
Hey, if my function, if this is a derivative of a function, what's the antiderivative of that?
2.
No.
I take the derivative to get this. So would it be like this?
Over 3 plus 4x plus, yeah.
Yeah.
What do you notice?
That. Yeah.
Such a connection. I really don't know.
I don't get the connection.
Well,
Other than that, the first term is divided by 3.